Welcome to Inorganic Chemistry. In this lecture, we'll introduce molecular orbital theory and look at simple homonuclear diatomic molecules. We'll divide this up into some sections, but this gives you an idea. We're going to cover starting from the LCAO theory, or approach to molecular orbital theory, and then we'll talk about simple diatomics, hydrogen and oxygen, and in that context we'll do molecular orbital energy level diagrams and bond order calculation. And we're going to do heteronuclear diatomics, carbon monoxide, and we'll introduce the idea of orbital potential energies and how to use those for hybrid orbitals. And finally we'll look at more complex molecules, ammonia, and we'll learn how to do symmetry adapted linear combinations of atomic orbitals and look at the frontier orbitals you get from the molecular orbital energy level diagram. Okay, let's look again at dihydrogen. We review Lewis' theory for how to do a bond, but let's look at how to use the results from quantum mechanics to understand a chemical bond. So a diagram of the hydrogen 1s wave function. So if this is the nucleus here, then we know the orbital has exponential decay away from the nucleus. Now in the molecule H2, we're going to have two atoms that have this wave function coming together. So let's draw that here next to this one. So we have another hydrogen atom here, another nucleus here, so it also has 1s orbital decaying exponentially away. As you bring these two together, you can see that the hydrogen 1s orbital on one atom is going to start to overlap with the hydrogen 1s orbital on the other. We're going to get overlap here between the two nuclei, and an easy way then to understand why this would create a bond between the atoms is that this represents electron density. Electrons are negative, nuclei are positive, so this nucleus is attracted to this electron density, which is attracted to this nucleus, so it holds the two atoms together in a chemical bond. So we could draw that this way, again, as the two wave functions overlapping here, positively, building up electron density between the nuclei, or you could view it top view, or top view. You have one hydrogen atom with the s orbital and another hydrogen atom with the s orbital, and they overlap positively to create a bond, or you can draw this mathematically, the wave function by the positive combination of some coefficient times the wave function representing the hydrogen 1s orbital on one atom plus the same coefficient times the wave function of the hydrogen 1s orbital on the second hydrogen atom. So this is an example of a linear combination of atomic orbitals. This sigma phi 1 plus phi 2. It's a linear combination in terms of algebra, what we're doing. And this is the idea behind the linear combination of atomic orbitals approach to molecular orbital theory, or LCAO. If you can do a positive linear combination, you could also do a negative linear combination. You could have a wave function that's made up of the same orbitals, but now instead of adding them together, you subtract them from each other, and this would be the antibond. So if adding them together creates electron density between the nuclei, subtracting them from each other creates a node between the nuclei. So we have our orbital on one atom, and then we're going to subtract hydrogen 1s orbital on the adjacent atom. So right there we have a node between the two nuclei, so we have less electron density between the two nuclei, so that is anti-bonding. Okay, so that's the idea behind the linear combination of atomic orbital approach to MO theory. And this allows us to take what we've learned already in terms of the shape of atomic orbitals, the energies of atomic orbitals, and put them together to describe the bonding in molecules. And this all comes from quantum mechanics, so there's a lot of calculus behind all this, but we're just going to look at it in this kind of linear, more superficial way so we can use the products of this approach. So the idea, or the tenets of this theory, are that molecular orbitals exist in molecules that describes the bonding, and they behave just like atomic orbitals. So they feel like atomic orbitals. They're made by the linear interaction among the orbitals of the atoms of the molecule. You're only going to use the valence atomic orbitals to make the molecular orbitals. So we're going to ignore the core atomic orbitals. They're lower in energy. They're buried inside the atoms. Just like we learned about atoms, their properties are understood in terms of their valence electrons, because that's where the chemistry takes place. So that same idea, we're doing chemistry here. Okay, the number of orbitals is conserved. So another way to think of this is the number of orbitals you use to make the molecular orbitals, number of atomic orbitals that you use is going to equal the number of molecular orbitals. And we saw that in the case of the dihydrogen. We had two hydrogen atoms, each with one atomic orbital. So we combined those. That's a total of 2 atomic orbitals that we used. So we had to have 2 molecular orbitals, and we saw we had the positive overlap one and the negative overlap one. So we had 2 molecular orbitals for dihydrogen. Okay, well, how do we combine these? We're going to combine them in a linear fashion, but which ones do we use? Where? We need to use our ideas of symmetry. Only atomic orbitals with identical symmetry can overlap. And the orbital overlap is maximized when the atomic orbitals have similar energy. And you'll work with that, kind of work through that in your worksheet in class.